recording, and I'll make sure to actually share the screen this time and not forget that. And we'll switch over to here. Good morning, everybody. Welcome back to Big Data. Hope everybody's spring break was nice and relaxing, and you are refreshed and recharged for the second half of this course. We've had a little bit of I guess a bigger break from this course because of the paternity leave that I was on for a little bit. We're going to be really hitting the ground running today. If you don't have a copy in the back of this big packet with 50 questions in it that we'll be going over today, get one of those. On the so we're on the week 9 folder today in our course repo, and that packet corresponds to the notes.pdf file. So you'll want to have that file open if you don't have the packet in front of you. And then before we get started today, just 2 real quick announcements. First one is that so today there's not going to be office hours during the normal office hours time, just because the math department has a meeting during that time, so I'll have to be going to that. If you do have office hours-y sort of questions, then either just like right after class or waiting till Wednesday to ask those. The other announcement is this Friday, so technically Thursday is Cesar Chavez Day, but it's being observed at CMC, the Claremont colleges, on Friday. So normally we would have that Friday class session and office hours, but we won't have that this Friday. So we'll have a little bit less work this week as we sort of get back into gear for our things. Before we get into material, this new material for today, on the week 9 folder, I have at the top details about the midterm. Everybody's midterm is graded and posted in Sakai, so you can go take a look at that. Here's the overall grade distribution. So the median grade for the midterm ended up being a 79%. And previously, before the midterm, the median grade in the class was in like the 95, 96 range. Post midterm, so currently with everything graded in the first half of the course, the overall median's an 89%. So overall, I'm pretty happy with how people are doing in the course, how grades are going. If for whatever reason you're not, let's say, in a minute we're going to go over some of the highlights of the midterm. But just as a reminder, for whatever reason you are not happy with what your grade is in this class, there is a bunch of extra credit that's already been posted. I'll be posting more extra credit later on as we go this second half of the semester. And you should always feel free to approach me and say that, oh, my grade is currently a B. I really want to get into the A- range, and what can I do to get that extra credit? And I'd be happy to give you sort of a personalized assignment that I think speaks to whatever it is that you need to work on. But yeah, my philosophy for grades is that the grade at the end of the class should reflect your knowledge at the end of the class. And so if you can demonstrate that you have mastered the skills, then I'm happy to give you a good grade. Okay, so about the midterm, some grading rubric highlights. First of all, the solution is posted onto the that same Padilla midterm repo, but now there's a new branch, the 2022 Spring Solution branch. And so here, if you click on the sequel, you can see what any of my solutions look like to the problems. And there we go. So the main ways that people lost points are all listed here. So some minor things, if you were missing things in your where clause, like, I don't know, swapped an and or an or missing a not, something small like that, just a -3. Most of the questions asked you to remove duplicates somehow. If you forgot to do that on a question, that was a -3. This one right here is an important one, and so I want to talk a little bit about it. That anytime you are working with a table, you want to make sure that that you're using the unique keys appropriately, things that are unique versus things that are not unique. In the film table, for example, it turns out that the title does not have a unique key. It does not have the unique constraint on the films. And that means that you could have multiple films with the same title. And because of that, if you ever have a select query or some sort of intermediate computation where you're extracting out the title from something, I mean, that's not going to give you the correct answer because you'll find this will get, maybe there's 10 films with the same title. This will get one of those films right here. But then when you do where title is up here, this will get you the other 9 of those films. So you always, in your intermediate computations, whenever you're doing a join or a subquery in an intermediate computation, you want to make sure that the thing that you're selecting from is unique, and almost always it should be a primary key. So the film ID would be the thing to use here. The film ID is the unique way to identify a film. Seems like a title might be a unique way, but it turns out that it's not. So that came up a lot in problem number 2. This is just an example of somebody's solution. And also in problem number 3, here's another example of somebody's solution subquery with selecting the title instead of a film ID. This is an important point that will, in the future, like real world scenario, you're implementing things, this will save you lots and lots of headaches if you get into the habit of using the actual unique things in these inner computations. So are there any questions about that? Is everybody awake this morning? Okay. Let's see. So then the main way that people lost points, the big point breakers were problem 1 and 4. Those were the 2 hardest ones. For problem 1, this was a very common sort of a style of a solution for problem 1 where you just had a bunch of joins together and then where conditions down here. It turns out this doesn't actually get you the correct solution. It includes way too many films that the real correct solution needed to use subqueries, or the easiest way to do it was to use subqueries to accomplish parts 2 and parts 3 rather than a where clause. It is possible, this was a very clever solution by Lulu, to use the except except clause to subtract out results like this, but somehow you had to actually be sort of subtracting results instead of filtering results. And then problem 4, this was another sort of common solution to problem 4 using a subquery inside of here, and this doesn't turn out to get you the right answer. My solution uses a self-join as the way to get the right answer here. I'm not going to go into too much detail about these because everybody's solutions have slightly different things that are wrong about them. But if you do have questions about why your solution, what you put, is not exactly the same as mine, you can look at the example solutions I have here, compare them, see that they're different, or come to office hours or after class today and we'll talk about it and work through it in detail why your solution wasn't right. And it's possible that I made a mistake and that you did have a correct solution. For most of these, I just eyeballed it, and if it looked like it was right or wrong, trusted my instincts. Very few of the solutions I actually copied into Postgres and ran them. So it's possible I made some mistakes. So you should double check my work. And then problem 5, people did really well on problem 5 overall, but some common mistakes were that, so the care 256, this still has type length of -1. And a lot of people put this at the very top of your table. It should go at the bottom. Technically, because the char type here is going to pad with a bunch of spaces, it's always going to take up 257 bytes, but that's still going to mess up the alignment of everything else. So this really should be at the bottom no matter what. And then a lot of people miss that the UUID has type length of 16 and just put it in a weird spot. Those are the two most common mistakes on problem 5. And the second part of 5, people did pretty well overall, very few mistakes. Any questions about anything from the midterm? Okay. Hopefully we're, yeah, if you do have any questions, then I'd be happy to go over your particular solutions and what's right and wrong about them one-on-one. But otherwise, we'll be moving on to new material now. And so again, first part of the course, everything that we've done so far, the main purpose has been to, well, at the very beginning, we were using Docker to just like get our databases up and running and making sure that we can do that, sort of run multiple of these virtual machine Docker images, containers, and get our database instances running. And then we spent a couple weeks just making our SQL code correct, given some database that already exists. And this assignment that you've had over spring break, we've seen started working on inserts and seeing the difference between the normalized versus denormalized inserts. And the thing that we've seen so far, or that once you finish that homework that you will observe, is that the normalized inserts, for what we have so far, are a lot slower than the denormalized inserts. And so the next about 2 weeks or so, we're going to talk about why that is and how to fix that to make them actually fast. And the first thing that we're going to be talking about with making those things fast is making them concurrent. So being able to run multiple inserts at the same time and having it all work. In your last homework assignment, we just had like there was just one zip file, and you were just inserting that one zip file sequentially, not doing any parallelism. But in that MapReduce assignment that we were working on sort of beginning of the semester, there were 1,000 or so zip files, and you had a different process inserting each of those to get that sort of potentially 1,000-fold speed up. On the Lambda server, there's only 80 cores, so you got an 80-fold speed up on the Lambda server. And we want to be able to achieve that 80-fold speed up again when we're inserting into Postgres. And so that's, we're going to be talking about the difficulties of that today. And so this Indiana Jones picture right here, like, why did it have to be concurrency? Concurrency turns out to be really one of the hardest problems in computer science. Yeah, and I guess we will see why that is today. But if the things that we start talking about today feel hard, then that should be expected. If they feel easy, then maybe you have a misunderstanding of what's going on. So what we're going to be focusing on today is there's this notes.pdf file. Again, in the back, there's the big packet, and that corresponds to the notes.pdf file on the GitHub repo. And that's what we're going to be going over today. This will be the basis for a quiz, probably Wednesday next week. But we'll decide that once we finish the file. And on the quiz, you'll be allowed to have arbitrary references. So in particular, you'll be able to have your laptop open and browse the Postgres documentation. These two links right here are going to be the main documentation that you'll be using for this quiz. But you will not have access to the actual Postgres server to type in commands. So you'll have to be able to sort of, in your head, type in the commands and figure out what's going on, referencing the documentation. And in class, we're going to talk about just sort of the some of the big picture ideas here, but we're not going to go over like all the detail things. And so you really will have to reference the documentation in order to be able to, say, complete that packet and understand all the problems, or the problems that I give you on the quiz, be able to complete them and do well on them. And the purpose of this, again, concurrency is an important thing, but reading documentation, especially documentation about hard, complex problems, also an important skill. And so we're trying to develop that practice of being able to read the documentation. Any questions at a high level before we get started with the technical details? Are we all ready for technical details? Everybody's awake, has coffee. This is yeah, should expect this will be a intense, mind-bending class today. So what I have open here on the left-hand side, two terminal windows logged into the Lambda server like normal. And then on the right-hand side, I have our PDF file. And what I want to do, I'm going to open up two separate P-SQL connections into a Postgres server on the left-hand side here. Everything that we've seen so far has been only with a single connection, a single session, but now we're going to do two sessions and see how that makes things complicated and all the different issues that arise. So the first thing that we have to do is we have to actually create our Postgres session. And you see that, let's go ahead and make these terminals a little bit bigger while we're doing stuff in the terminal for a second. See that we currently have no Docker processes running, and so we need to start a sort of a blank, empty slate Postgres. And I'm not going to be using Docker Compose for this. I'm going to be using regular Docker. And I recommend, again, as you're going through this this quiz, to sort of check your work. You can I'll show you how to check your work by typing the things into the terminals over here. And you'll want to be following the same procedure with having Docker open the way I'm going to run it now. So I ran Docker PS. There's currently no Docker containers running. I'm going to Docker run Postgres. So Postgres is an image that comes from the internet. And if we do this, we get this sort of scary error message saying we can't just run it by itself. That we have to, for security reasons, the Postgres image requires us to somehow specify a password or how we're going to access this, this image, this container that gets created by the image. In this case, there's nothing security related about this. It's just going to be a totally temporary thing. So this this line right down here says that you don't need a password or any authentication to access the server. So that's what we'll use. So Docker run Postgres, -E, E stands for environment, to pass in the environment variables. And I'll paste that right here. And now we can run Postgres. And now it's actually running. And you can see that it's started up and now waiting for connections. Not quite what we want. We want it in daemon mode so that we'll be able to open up P-SQL. That the database itself will be in the background. So I'll press Control-C right now. Stop that up arrow, come back here. Move over back to the run command. And if you recall -D right here, D for daemon, will send this to the background. And this hash right here is the hash for the resulting container that just got ran. And if I do Docker PS, now we can see that there is a running container. This is the hash corresponding to that container. And now I can execute my P-SQL command connecting to this container, Docker exec-it, and then the container hash like this, P-SQL. And so we're almost there, but we're still getting an error message. It says, so we know that we're successfully connecting to the container right now. Maybe I can double verify that, typing bash. It's actually connecting to the container in the container. Let's exit out of that. So this is connecting to the container, running P-SQL in the container, and this error message is from P-SQL. It says the connection to server on sockets, blah, blah, blah. Fatal role root does not exist. So by default, anytime you're running the P-SQL command, it tries to log into the database using whatever the username is that you're currently logged in as. When you use the docker exec command, all these commands get run as the root user, but Postgres requires by default that you log in using the Postgres user. So -- user equals Postgres like this. And finally, we have successfully connected to Postgres. Up here, \d, we can see that there are no relations. It's a totally empty Postgres server. And here is our successful connection command. I'm going to copy and paste that down here. So now we have two successfully created, or two successfully connected Postgres sessions. Both of them do not have any relations. Let's just one more thing before we stop for questions. I want to make sure that these are actually connected to the same Postgres instance. So what I'm going to do is I'm just going to create a real quick table, create table T, and it'll just have something, I don't know, it's just a dumb little table like this. Up here, I type \d. We can see that the table now does exist. Here's the name T. Down here, type \d. We do have access to that table. So these are both connected to the same Postgres database, and we can run commands in either one of these two things, and it will take effect into the database. Any questions about what our setup is, or anything so far? This is an important thing to be able to reproduce in order to be able to work on this quiz. So it's okay if you don't feel like you've memorized all those procedures that I just typed in. Everything's going to be recorded. It is being recorded, so you can go back and see those if you need to. But you'll need to be able to do this to check your answers on the quiz. We're all good? Ready to move on? Questions? Okay. So on to the quiz. Let's see. Is this text over here big enough that people can read it, at least with referencing the printout in front of you? I don't know that there's enough room to be able to make this too much bigger, but I can try if people need to. And so don't be shy about asking to make it bigger. But one of the things that you'll see on here is that there's two columns of commands, and each command has a number associated with it. And so for every particular number, so like the number 1, there'll be a command only in one of those columns and not in the other column. And as we're going through each of these problems, the idea is that we sort of, like, these numbers represent time. And so we type all of these commands one at a time, going from top to bottom into these sessions over here. Say that this top session is session number 1, and this bottom session is session number 2. And some of these commands will go into the top one, some will go into the bottom one. And we'll see how things are different depending on the order that these different commands get run in and the actual commands themselves. So in order to make sure that I have a back to a blank blank database, all of these problems are assuming that there exists nothing in the database at the very beginning. I'm just going to drop the drop table T. That's how we delete a table in SQL. So no relations, no relations. So we're in a totally empty database right now, and that's the state that you want to be in when you start one of these problems. So for this problem, session 1 right here says create table T, and so up in the top, I'm going to do create table T a int like that, and we created the table. And now down over here in session 2, we have this select count star from T command. So down here, I'm going to type select count star from T like this, and we see that the answer that we get is 0. The instructions for these problems, we'll talk about what this number 1 and number 2 mean in a little bit when we get to them. But number 3 says write the output of each select statement. And so we just had a select statement over here. The output of all these select statements are just going to be like count star from t, so it's just going to be a number. So you don't need to worry about the formatting. You can just focus on the number down here. And what we're going to do is I'll just write the number like that, 0 next to that, because we got 0 as the output from this select statement. And then, so that was command number 2 that we just did. There we go. A little bit bigger so we can see the numbers over here. And so we just did command number 2. Now we're on to command number 3. Over here it says insert into t values 5. Oops. And again, so I almost made a very critical mistake. We need to be very careful about which session we're typing things into. I said session 1 is going to be the top, and session 2 is going to be the bottom. So over here, this number 3 is under session 1. So the insert into t should come up here. Insert into t values 5, like that. And then we have number 4. Insert into t values 6, like that. And then we're on step number 5 down here, another select statement. So down here, select count star from t, like this. And we can see that the count is now 2. So I'm going to write a 2 over here, like that. And the important thing about this that we've seen is that it doesn't matter where you create the tables. It doesn't matter where you insert the tables. The results are going to be visible in all of the different sessions, no matter what session you're connecting to. If it's from the top or from the bottom, the results will be visible. So one more insert statement up here, inserting 2 in session 1. This is line number 6. And then one more select count star from t, line number 7 down here, and we get a number 3. Any questions about like the format of these problems, or why these are the right numbers for this problem, or anything at all so far? Does all make sense? Pretty straightforward so far? Okay. Lots of head nods, that's good. So at this point, yeah, everything is sort of commands that we've seen before, and this is probably like, I don't know, what if you were to just guess numbers, this is probably what you would have guessed would have happened. Things will start getting a little bit trickier in problem number 2. Here we add this new syntax of the begin statement right here and this commit statement. So the only difference between problem number 1 and problem 2 is that problem number 1 did not have begin and commit, and problem number 2 does have begin and commit. This, anytime you see the word begin in SQL, what is beginning is a transaction is beginning. So anytime this is a key vocabulary word, anytime I start pSQL, each pSQL is a different session. And one session can have many transactions because I can type the begin keyword many times in an individual session. And so it's easy to get these two things confused, but each pSQL or each connection in Python, pSQL or Python, anything that's connecting to the database somehow, that's a session. But the actual SQL command begin initiates a transaction. And you'll see both of those words used in the documentation a lot, and so it's very important to get those clear. Now we'll see exactly what this transaction does. So in order to start problem 2, again, I need an empty database, a blank database. And I don't have a blank database right now. I have this this thing up here. I have this table right here, so I can drop table T like that to get me back to a blank database. And now I can start problem 2. So here, problem 2, step 1, again, the same thing as before, starting with the create table T, A, int, like that. And then session 2, we have our select count star from T, just like before. And so we get a 0, just like before. Lines 1 and 2 don't change between problems 1 and 2, so we get the same answer right here. But now, line 3 is something new, the begin statement. So begin up top. And now we do commands 4 and 5. So 4 is insert into T values 5, and insert into T values 6. So now I've inserted these two values into our table, but I've done that inside of a transaction. And so now the question is, what's going to happen over here outside of the transaction when I run the select statement? And the answer is, it's not going to be visible. So I'm going to run the select count star from T in session 2, hit enter, and you see that the result is still 0. So I'm going to break away slightly from the problem up here by running a select command at the top. Select count star from T. So this select command is not actually in the in this list of commands over here, but it's a select statement, so it's not going to change anything. But you can see that if I'm inside of the transaction, I do still have access, able to see those rows. It's just the fact that session 2 is outside of the transaction, and so it does not have access to see those rows. Let's go ahead and run line 7 now. Insert into T values 2. And then line 8 is the commit. Commit like this. What commit does is it says all of the things that we've done inside of our transaction, in this case, all of the inserts that we've done, make those visible to everybody else. And so after this commit, after line 8, when we run line 9 right here, select count star from T, now we do in fact have access to being able to see those. So because line 9 over here happens after this commit over here, we are able to see the results. So the big difference between problem 1 and 2 in terms of the output is this right here. On the first one, no transaction, it was a 2. It was able to see these inserts. On this problem 2, we're inside a transaction when we're inserting, so we are not able to see the results over here. Any questions about that? Yes?
What happens if you try to modify the table when the transaction is happening?
Great question. So the question is, we have a really simple example here of there's just like inserts on one side. What happens if we had inserts in multiple sessions? And that's like problem 30 or so that we'll get to that. So that it's going to be slowly building up these more complex situations. The answer is sometimes that's allowed, sometimes it's not, and we'll have to think really carefully about that. Good question.
Yeah, maybe you missed it, but why is this whole transaction and sessions thing necessary?
Great question. The question is, why is this necessary? Fantastic question. We'll be able to answer this more fully after we see all the examples of what we can do with transactions. But basically what this is going to do is it's one of the key words, one of the key vocabulary words is that transactions are atomic. And atomic means that anything that happens inside of a transaction, either everything happens or nothing happens. And so if you think about our Twitter assignments, where we have a bunch of different tables, and for each tweet we need to insert into many different tables, it would be really bad if like we started inserting into the users table, but then power cut out before we were inserting into the tweets table. And so we only partially inserted a tweet. And transactions are going to make it so that we're guaranteed to either fully insert the tweet or fully not insert the tweet, even in the event of like power outages or major disasters like that. The canonical example of, and this is the example used in the documentation about why you would want to use a transaction, is that if you're a bank and if one customer is sending money to another customer, you don't want, if one balance goes up, the other balance must go down. You can't have one balance change without the other. So anytime you need two events to like either fully happen together or not happen, that's when the transactions come. And we'll see more examples of that after we see the capabilities. Question, Karen?
So that's like, so you don't mess up your database if the characters that.
Because
then you'd have like partial.
Yeah, so the power goes out is like one example, but it's not necessarily just power going out. It could be like, there could be like logical reasons as well, not just like disaster reasons. This next problem number 3 gets into these logical sort of situations. And the difference between problem number 2 and problem number 3, the only difference is that in problem number 3, instead of having a commit, we have rollback down here as the command on line 8. And so let's see what's going to happen with that. Let's go ahead and drop table T again. So we're back to our empty database and create table T down here. Select count star, we still get a 0. Up here, begin, then insert into T values 5, insert into T value 6. Down here, we're on line 6 right now. Select count star from T, still a 0. I'll go ahead and write these numbers over here. We got 0 for the first one, 0 for the second one. And we just finished line 6, so we're on line 7 now. Insert into T a value of 2. But now instead of doing a commit up here, we're just going to do a rollback. And what a rollback does is it says, forget all the changes that you made, forget all the inserts, deletes, updates, whatever you did inside of the transaction, forget them, go back to the normal state. And so down here on line 9, we just finished line 8, so we're on line 9 now. I run the select count star from T, and we get 0 again. So even though we have a whole bunch of inserts over here, because it was in a transaction and the transaction ended in a rollback, we still maintain a 0 down here at the end. So it's like nothing happened. Any questions about what the rollback does?
Again, I'm always thinking about this in terms of like implementation in like an app or something.
Yep.
So why would you do this in the first place instead of like doing nothing?
Yeah, so the question is, why would you do this in the first place instead of doing nothing? So one example here, let's say you're a web page that has a shopping cart. Every time somebody adds something into the shopping cart, you might insert into the shopping cart. And then when the person actually like pays and checks out, that might be when you commit your changes. Like, okay, they've actually purchased these things now, they're no longer in the inventory. But maybe the person never does a checkout. They just like walk away from their computer, and you don't want to leave that stuff in limbo forever. So maybe you have like an hour grace period that the person's allowed to have stuff in their shopping cart before you return it to where other people can check it out. And so after that hour period, the person hasn't checked out their shopping cart, you have not issued a commit, so you choose to roll it back. You didn't, that's like an application logic specific thing. You could have kept it in the transaction there indefinitely, but then, yeah, we'll see that introduces more problems later on. Basically, other people would not be able to purchase those things. Yeah, great questions to be thinking about applications that helps solidify like all of these sorts of things. Any other questions at this point? Okay, So there are 3 commands that can be used to end a transaction: commit, rollback, and abort. I'm not going to tell you what abort does. This is going to be the first example of something that you'll have to look up in the documentation about what happens when you do an abort. And so you can, you should both type this into Postgres over here and see what the results are. And you should read the documentation to see like what the edge cases differences are between abort and rollback. After you've done that, if you have questions about it, then I'd be happy to answer those questions. But I don't want to answer those questions until you have to like show me, here's the line in the documentation that I'm not 100% sure about, and then we can talk about what that documentation is trying to say. Any questions about that? Okay. So I think most people like the transactions by themselves, like they eventually, I don't know, it becomes intuitive eventually. This isolation levels is the first concept that will never be intuitive, right? I've been using this for, I don't know, like a dozen years, and isolation levels are something that I still have to constantly refer to documentation about because there's just nothing intuitive at all about it. And so here, the difference between problem number 5 and the previous ones is that we have 2 transactions. On the left, we have the same transaction that we had before, that all the insert is happening in a transaction. And then on the right, we have all of our selects are also inside of a transaction. And we want to see how this transaction affects what goes on with these select statements. So again, we have our, let's go ahead and drop table T, get back to our naked database and create table T. So that was line 1. Line over 2 here is now going to be begin on the session 2. And then a select count star, still a 0. So let's add our 0 over here. And then line 4, another begin, and then our inserts into T. Let's see, the very first one is a 5, and then we'll do a 6. And then down over here, we're going to rerun this select command like this. And we'll see that this select command right here still gives us a value of 0. The reason it still gives us a value of 0 is because of this transaction over here on the left. Yeah, but we haven't committed the inserts over here, so this is still a 0. And so now let's add our next insert, line 8, to like this. And then line 9, commit, make all those changes permanent. And now we're on line 10 down here on the right-hand side, select count star, and we still get a count 3. So the fact that these selects are inside a transaction has no effect on what these selects are able to see. And then the fact that we have a commit down here, line 11, that commit does nothing because there were no changes made in this transaction. So this transaction by default has no effect on these select statements. But that's by default. Now we're going to see a special type of begin statement that has this isolation level of repeatable read. What repeatable read means is that you're guaranteed if you run a command once, you're going to get that, like run a select command once, you're guaranteed to get the same results when you run it again in the same transaction. So up here, /c, run our drop command, drop table T, run our create command, create table T. Then on the right-hand side, down here, begin, isolation level, repeatable read. One sort of subtle thing about this is notice that there's no semicolon at the end of line 2 over here. So I've combined it, line 2 and 3, just into the same line down here. The semicolon is what indicates the end of a SQL command. And so I just happen to put it on the same line. It's okay. Begin isolation level, blah, blah, blah. And now when I run my select count star from T, I've run the select count star from T. And what repeatable read means, again, is that when you, you run a command once, you're guaranteed to get the same results for that command throughout the rest of the transaction's history. So on the repeating all these commands now, begin number 5, number 6, the insert into T with 5, and then 6, and then on the right-hand side, select count star from T, still get a 0. We still get a 0 here again because, same reason we did before, 0 and 0, get a 0 here because of this transaction over here. We would always get a 0 here no matter what the isolation level of this begin transaction is up here. We're on line number 9 right now. Insert T values 2 in the top transaction. Let's commit that transaction. And now down here, we're on line number 11, select count star from T. And now we get something different. We get a 0. This is different than what it was before. So arrow different. Because we're in a transaction that has an isolation level of repeatable read, this is going to be different. And then down here, we'll commit. And I don't have another select count star. I should have put one. Let's go ahead and run it. Run a new select count star, and we get 3. So if we add another select statement right here, ... that would give us the value of 3 because it's outside of the commit. So the repeatable read means that everything inside is going to be the same no matter what. Any questions about what repeatable read is doing? Sorry? What if we inserted something? Great question. So the question is, what if we had an insert over here? The answer is, let's go ahead and do something like that. So let's do a begin. Up here, down here, there's our begin isolation level repeatable read. Select count star from T, 3. Let's do an insert up here. Down here, select count star, still 3 because this has not been committed. Let's commit this. And still 3 because it is a repeatable read. And so these two things must be the same. If I have an insert now, so let's do inserts into T values 10 like this. Now that insert is going to be seen, and the select count star from T will consider that insert. So yeah, what I said before was that a command, select command, is always going to give you the same results, independent of what happens in other transactions. It's not fully correct. It's that it's going to give you the same results, but then modified by whatever inserts happen inside of that particular transaction. So that's a great question. Did that answer your question? Cool. Yes.
What's the point of a repeatable read if everything is the same as?
Professor, I have a question.
1 second, hold on.
Okay.
So the question is, what's the point of the repeatable read if everything is the same as the first select? And so like we could think about maybe we're doing this in Python, and maybe if I actually wanted to get the same value, I would just store that in a temporary variable and then just use that temporary variable later on. And so that is, like, from a good software engineering principles, a good thing to do. It turns out, though, that, I don't know, when you have a giant project with like millions of lines of code, you might not know whether somebody has done this already or not. Repeatable read, it's not just the same command that will give the same results. It turns out to be slightly more subtle than that too, that it's anytime you access the same row, it's going to give you the same results. Count star happens to access all of the rows. So yeah, in this case, this particular example could just be replaced by, in Python, temporary variables. Again, more complicated situations are coming up though. So these are just like illustrating the big picture points at this point.
So it's the same result for the exact same command, or like the same row.
Guaranteed to be the same. Guaranteed to be the same result for the exact same command is one of the implications. Technically, the what repeatable read means is that when you read an individual row, you're guaranteed to get the same results on that individual row. So maybe at one point I want to do a select count star, but then at another point I want to do a select star from T where A equals 10, like that. And so this and this one here happens to access this row right here. If this row was deleted after this happened, though, then this will still be guaranteed to exist. Yeah. So I guess it's great to be thinking about the weird edge cases. Not quite fully at the point where we can fully resolve that yet, though. So Hanan on Zoom, you had a question?
Yeah, I wanted to know what is the beginner's isolation level and repeatable read does, because like I didn't really hear it.
What does what do?
The line number 2 and then line number 3 of the section 2.
So question from Zoom is line number 2 and 3. What exactly are they doing? The first thing to notice is that line number 2 and 3 are it's just one command. It's not two separate commands because there's no semicolon over here. And this whole thing is like it's like a one noun by itself. You can't there's no such thing as like begin isolation repeatable read or begin isolation level repeatable. You have to type this whole thing together as itself, and all it does is it starts this new type of transaction with this new type of property. So you will either see begin or begin isolation level repeatable read and nothing else to start a transaction. So while we're talking about the differences between these two different isolation levels, now's a good time to check out the references. And this first reference here talks about the transaction levels. And so if we visit that, for the quiz, what you're responsible for is these two sections right here. The read committed isolation level, this is the default isolation level. So when you use just begin by itself, this is what's going to happen. And when you use the begin isolation level repeatable read, this is what's going to happen right here. And inside of the documentation, it has lots of examples about where like the weird edge cases are going to come up. So you're responsible for reading this and understanding it and seeing how it relates to some of the later problems. It's not too long, just like maybe 2 or 3 pages printed, but it is quite technical.
All right, thank you, Professor.
So now we're going to shift gears for a minute and talking about something called locking. Locking will turn out to be, so this is sort of like the main, for our purposes in this class, this is the most important thing that is going to happen from this quiz. And everything else about this quiz is somehow relating to locking. Very end, very last section, that last like 2 or 3 problems, combines locking with repeatable reads. The way this is going to come up in your programming assignments is that your next Twitter assignment, you're going to be doing a parallel concurrent insert into the Postgres database. And there'll be several different types of databases that you're doing this into, and they will all have different types of locks going on inside of them. Based on how the database is structured, and we'll see how that has all sorts of different performance implications based on what we see in this quiz right here. So this is going to give us the just like the technical mechanics here, and your next programming assignment is going to try to flesh out the applications of why do we care. So there's a new command that we're seeing here on line 3, this lock table command. And the lock table command, the format of it is that it has the name of the table and then in and then a mode. In this case right here, it's saying in exclusive mode. And I'm going to take a look at the documentation again. So this explicit locking documentation right here tells us everything that you need to know about locks. For this, this documentation, you need to know these two sections, table level locks and row level locks, and this section down here, deadlocks. This table level locks is the most important one. This is like 95% of all the problems are related to this one right here. And in this table level locks, there's, for this first section of the quiz, this explicit locking, this is the table that you need to understand how to interpret this table. Let's go ahead and make our database empty again, drop table T. And now let's restart here. Problem 7. And now we've totally shifted gears. These problems are not related at all to the previous problems. I guess they have the same create table T, but that's it. Create table T, a int like this, line 1 right here. Then line 2 begin. And then line 3, lock table T in exclusive mode. So lock table T in exclusive mode. And so what's just happened now is that table T is locked in exclusive mode. Up here, under this existing lock mode, we can find exclusive right here, EXCL standing for exclusive. And any of these modes down here, if we try to lock the table in any of these modes, because it has an X right here, that means we won't be able to do it. So the top, this up here, your existing lock mode, our existing lock mode, our current lock mode is the exclusive mode because that's the first lock that happened. And now on line 5 right here, we're going to try to lock it in share mode. When I try to lock it in share mode, so here is share. We have an X right here. The X means you cannot lock something in share mode if it is already locked in exclusive mode. So let's see what happens. Down here, begin. Lock table T in share mode. Like that. I hit enter, and you can see that Postgres now just hangs. And it will hang indefinitely until the vocabulary term is until this lock is released. There's only one way in Postgres for our purposes, there's only one way in Postgres to release a lock, and that is to end the transaction. Doesn't matter how you end it. It can be commit, abort, rollback. But once the transaction is ended, then the lock is ended. So down here, I'll type, or let's see, we just typed line 5 down here, lock table, and then line 6 is commit up here. And so pay attention down here to what's going to happen. As soon as I commit up here on the top, I'm going to hit enter. And down here instantly, as soon as I hit enter, as soon as I commit this transaction, this lock left, this lock was freed, this lock was released. And so now because that lock was gone, this lock was allowed to take effect. And now this table down here is locked in share mode. And then commit down here to end our problem. In order to, or what this problem is actually asking you to do, let's go scroll up to the top for a second to the instructions. It says circle all the SQL commands that block. Anytime you try to get a lock and you cannot get a lock, then that command has blocked. So line 5 right here, this line right here blocked. So in that circle again, means that it blocked. And the vocab again, when you commit, when you ended the transaction, the lock is released. So one of the things that when we're doing our concurrency programming, trying to insert lots and lots of data rapidly, we will want to make sure, or we will do our best to prevent these blocking situations from happening, because that's obviously going to slow down our code a lot if we're just sitting there waiting for some other program to release its lock. Any questions about this problem 7 right here? Oh. Question is, can you only lock tables in transactions? And the answer is yes. Lock command outside of a transaction. So right now I'm outside of a transaction up here. If I run this command, you'll get this error saying that the lock table can only be used in transaction blocks. So for these explicit locks, there's a couple of different problems where it just has you starting in a different locking mode. And then it's you have to look in the table. Again, so here, this next one, we're starting in the share mode, and then we're going into the exclusive mode. Starting in share, so existing lock mode, starting in share. Let's see, where is share up here? There's share. And now we're going into exclusive. Here's exclusive. We have an X right here, so it blocks. The X means that it blocks. And so I'm not going to run this command down here. I'm just going to go ahead and circle this because I know it's going to block because we just looked up in that table. And let's see, here's a few more. So in this one now, we're starting in share mode, but now we're going into row share mode. Starting in share, going into row share. So starting in share, existing lock mode up here is share, going into row share. Row share here on the left-hand side. Come over, no X right here, so it does not block. And so there's no blocking right here. And so we don't circle that. If you want to be totally explicit, you can just say no blocking. So the reason for doing these problems right here, this explicit locking, is that what we're going to see next is that all of the different SQL commands that we can run, they will do what's called implicit locking, automatically creating certain locks on the table so that certain bad situations can't happen. And so these first problems right here are just getting you the practice of being able to look in that table, look up the different lock modes, and seeing whether something is going to lock or block or not block when you already know exactly what, like it's given to you what the modes are. Any questions on the explicit locking? Yes.
So for this question, why don't the last two columns matter in here?
The last two columns.
Yeah, for the share mode, or I guess the last two. And then if you go into the share mode, there's like.
So when you're referring to last two or last three, are you referring to the line numbers like 6 and 7?
Oh, sorry. Can we look at the diagram or look at the table? Yeah. So those last two columns.
Which exclusive and access exclusive?
For the row share mode, like why doesn't that?
Great question. So here, the question is right here, we're going into row share mode. And up here, we can see that, so row share mode right here, we could not enter row share mode if we already had an exclusive or an access exclusive lock on the table. In this case, though, we know that we have a share lock on the table because it says share right here. And so because it says share, I look at the share column right here, and that says it allows me to do it. If right here it said exclusive, then I would not be allowed to do it. Good question. Any other questions so far? Okay. So let's come down a little bit. So there's just a bunch of practice problems like this. So deadlocks. What a deadlock is it means that your program is not able to make any progress at all. That you have, let's go ahead and see this example right here. So let's make our database empty again, drop table T. And then up here, let's create table T. And then down here, so a difference on this one is now we have two different tables, a table T and a table U. Create table U, and like this. And now we're on line 3 up here. Let's begin our transaction. This is a normal transaction. And we'll do a lock table T in exclusive mode. And then no problems there. Over here, line 5, begin. And then line 6, lock table U in exclusive mode. Lock table U in exclusive mode like that. And that's totally okay. That exclusive mode, not compatible with exclusive mode, but these are two separate tables, so that's allowed. There's no conflict. You only have to look up in that table when you're locking on the same table as before. These are two different tables. But now up here, line 7 is what we're on. We're going to lock table U in exclusive mode. We first, line 4, we locked table T. Now we're locking table U. And line 6 over here, lock table U. So we're already locked table U in exclusive mode. Come back over to this chart. We're in exclusive mode. And if you're trying to lock in exclusive mode, you can't do that. The exclusive word should give you a sense that it's a very exclusive thing. You can't do a lot of locking if something's been exclusively locked. And so I'm going to come hit enter up here, and you can see that we're waiting. Can't make any progress until this transaction down here releases its lock on table U. But session 2 is not going to release its lock on table U. It is going to acquire a new lock on table T. Lock table T in exclusive mode. This is also going to block. So let's go ahead and circle 7 right here. 7 is what's currently running up here. It is blocked. And now we're about to run 8 down here. 8 is also going to block because it has, T is already in exclusive mode. And so I'll hit enter, and you can see they're both blocked. And this is what's called a deadlock. A deadlock is when the two transactions, neither transaction can make progress because they're both waiting on the same resources. Two transactions can't make progress. And sorry for the hard to read writing over here, but this word is progress. And again, the documentation has some more examples of things that can cause deadlocks, but this is the sort of canonical example right here. And when, for this assignment, when you get a deadlock, you're supposed to write the word deadlock down below. And then anytime you have a command that fails, that throws an error for some reason, you're supposed to put a square around that, is what the instructions say. So here, square around that, because that throws the deadlock error right here. We get that deadlock detected error. And up here, this lock becomes released because as soon as this error message happens, this transaction gets ended. So I guess I said before, the committing, aborting, rolling back are the ways to end transactions. Those are the explicit ways to end a transaction, but Postgres will automatically detect a deadlock for you and end the transaction if there's a deadlock. So deadlocks are obviously very bad things and something that we'll need to avoid in our programming assignments while we're inserting data. Any questions about deadlocks, what they are? Yes. Oh, yeah. Yes. I said do a square around it. You're right that the instructions say do an X on it. So I misspoke before. I said that do a square, but it should be an X so that it's more distinct from a circle. X, error, circle, block, and then the output of the select statements. Thank you. Any other questions?
So is line 8 also considered a block, or would you only consider it?
Yeah, that's a good question. So line 8 also, it first blocks, it both blocks and deadlocks. Anything that deadlocks is going to block. In terms of like quiz purposes, it's fine to put a circle and an X or just put an X. Either would be a correct answer. let's see. So then the other problems in here for this deadlock section just have different different modes, different access modes, different lock modes that you are locking the tables in. And so you have to understand, are the locks blocking or not blocking? And so will it cause a deadlock or not cause a deadlock? They also rearranges the order in different ways. So you have to understand how do the different orders of the different commands affect the deadlock ability of it. And so I'll let you try those out on your own and reference the documentation for those. We have about 5 more minutes left in class. We'll get through the this implicit locks 1 today, and then finish this up on Wednesday. So I mentioned before that all of our SQL commands will. The reason we did these explicit locks is so that you just have to look up in the table, like what is the actual lock mode to see whether something blocks or not. And from now on, though, like it's very rare to actually explicitly lock a table. And usually what happens is we run a command like an insert command or an update command. And those will implicitly acquire a lock on the table. We have to be able to go from this normal command back to what the lock is. In order to figure out what the lock for any particular command is, we go to the documentation up here, and above this table, still in the section on table level locks, it has this list of like the details of all of these table level locks. And under this, for each one of these things, the very first little paragraph tells you what the things it conflicts with are, so what all the X's are in the table. It's basically not worth reading this first paragraph. The second paragraph is the important one. It's the one that tells you what commands acquire the different locks. So here it says the select command acquires a lock of this mode on the reference table. So if you're selecting from a table, it acquires the access share lock. We're looking for the insert command. So here, row exclusive. This command, the commands update, delete, and insert acquire this lock mode. So we're running an insert command. So this is going to be a row exclusive lock. So right over here, this insert command is equivalent to a row exclusive lock. You don't have to write this out on the quiz, but it'd be helpful to go step by step like this. Insert acquires a row exclusive lock. And so now we have a table that's already in access exclusive mode, and we're going to acquire a row exclusive lock, and we need to know whether we can do that or not. So back over here, back down to the table here. We are already in access exclusive mode. And it turns out no matter what lock you try to do on access exclusive, you can't do it. So when we do the row exclusive, which is what we got for the insert command, we can't do it. So that's going to block. So right here, circle that because it's going to block. Again, access exclusive. We already saw that anything for access exclusive, you can't do it. The select statement is going to access share is the select statement. And so it's going to block because you can't, if a command acquires a lock and you already have an access exclusive lock, you can't do it. Here, getting a little bit more interesting with the share and doing an insert. So again, this is going to be the row exclusive. And then down here, select the access share. I'll let you look up those, how to do it. These will get more interesting down here when we get to the implicit locks too. Down here, the commands on the right are commands that you haven't seen before, probably. We certainly haven't talked about them in class. So like create index concurrently, vacuum, and vacuum full, these sorts of commands. And you'll have to look over here. So let's do a search, create index. We can see that create index concurrently acquires this share update exclusive, create index acquires share. So let's go back up here to the, so create index acquires a share lock. And the, yeah, so create index right here, create index, share, create index concurrently, gets share update exclusive, share update exclusive. And so if we're already in row exclusive, can we take out a share lock? Let's go look at the table. If we're already in row exclusive right here, can we take out a share lock? Here's share. It's got an X, no, so it's going to block. So this right here, go into block. Here we're row exclusive mode, taking out a share update exclusive. Share update exclusive, trying to take out a share right here, and can't do it. So this one's still going to block, and so on. Yeah, that's I think a good stopping point for today. My recommendation for our class on Wednesday is that you try to get fully up to speed on, make sure you understand everything up to like page 15, up to implicit locks 2, so that on Wednesday when we really talk about the weird stuff, you'll be in a good place for that. I'll be happy to answer more questions after class here, but that's the end of our time for today. And so, yeah, it was good seeing you all back from break, and I'll see you all on Wednesday.
Thank you, Professor.